Okay, this is good? All right. Hi, welcome to the LLVM register allocation talk. This is the most definitely censored and cut repeatedly talk about the register allocation in the LLVM framework. You don't really want to hear all the details. If you want, please read the source code. My name is Evan Cheng. As you can tell from my black shirt and jeans, I work at Apple. So the talk is going to be roughly broken down into 4 parts. First, I'm going to talk a little bit about why we care about register allocation. Kind of done. The next part, I'm going to talk about all the phases of the register allocator in LLVM. The next part, I'm going to talk about some of the optimization that I find interesting that we put in the last couple of years. Then we talk and look to the future and talk about all the works we're doing right now and we have planned in the near future. So why do we care about register allocation? It's kind of done, right? It works. The LLVM's code generate pretty good code. On average, on spec, just everybody knows spec. We do pretty well. I mean, I think without the help of LTO, we're about 5% better than GC support too. On 64-bit, we're about the same. We have some work to do there still. We do significantly better on some of the codec stuff that Apple cares about, for example. So this is obvious employment for Avid. So, but it's not quite true. So we do really care about squeezing out the last few % of performance from the generated code, and want to fix the pathological cases where the register allocator falls apart and do really bad things. But more important things is we care about the compile time for static compilation and even more so for JIT. And the last point is more important. We want to be able to enable more aggressive optimizations. What does that mean? Let's talk about LLVM design philosophy. We believe every optimization phase should be as aggressive as possible. And the later passes would just do the right thing and make sure the code doesn't get pessimized. How does it relate to register allocation? Well, some of the optimization phases that happen before register allocation can and do increase register pressure. And we want to make sure the register allocator can deal with increased register pressure and don't do really bad things. Example, we have a looping invariant code motion pass on the machine level. This is not turned on yet. Just look at a quick example. The V set 0 in the loop basically use a x86 SSC instruction to clear a 128-bit vector register. It's obviously a looping invariant. And machine LLVM just hoists it up into the loop preheader. This seems like a pretty obvious optimization, right? This means we only clear the register once and we use it multiple times without recomputation in the loop. However, moving something away from its use means increased life range. This increased register pressure. So it's not necessarily a good thing, right? It's possible increased register pressure means spilling the code. And the reload inside a loop can really kill performance of the generated code. Later on, I'll come back to this example to talk about how the register allocator can deal with this kind of situations. But first, let's take a look at the register allocator, all the passes involved. The register allocator is basically divided into 5 parts. The fee elimination and a true address pass move LLVM code out of SSC form. The Coalescer is responsible for removing a lot of copies. The linear scan allocator is basically the real allocator that deals with allocating physical registers to virtual registers. And in case we run out of register, spiller is there to help it spill registers. The rewriter has a simple job of translating virtual register into physical register using the decision that has already been made. Fee elimination, it moves SSC form, move LLVM code out of SSA form, right, and eliminate feed nodes. The current implementation is very naive. It basically inserts copies in all the source basic blocks. Then you replace the feed nodes with another copy. This works, but it introduces lots of copies, which the Coalescer will have to work really hard to get rid of. This is a compile time issue because the more work the coalescer has to do, the more time spent there. True address pass. Again, the true address pass move code out of SSA form. It convert SSA3 address instruction into instructions with read, modify, write operands. For example, x86, the add instruction requires the destination to be the same register as one of the source operand. So how does the LLVM true address pass deal with this? It's pretty simple. Again, it converts, insert a copy, then it does a register renaming. Pretty straightforward. The obvious optimization we can do here, but we won't talk about them today. Let's take a look at the coalescing. The coalescer basically eliminates copies by register renaming. The example here is pretty straightforward, but hopefully illustrates what it does. You see there's a single copy from V1 register to V2 register. And there are two vertical bars on the right that represent their life ranges. Basically, the starting point where they are alive, and end point basically is the last use. So V1 and V2, as you can tell, obviously overlap. However, the rest of the coalescer is smart enough to notice during the portion they overlap, V1 is not modified at all. So it is smart enough to rewrite them, turn the copy into identity copy, which will then eliminate. And the V1's life interval grows, but we get rid of one register. It's worth noting the implementation of the register coalescer is very, very aggressive. We do value numbering, which means we can coalesce a lot of overlapping life intervals together. After register coalescing, you see a lot of life intervals. They have multiple definitions, and they're represented by different value numbers. Here's somebody, I'm sure a lot of people have raised this question. So why do we do coalescing so aggressively ahead of time? Coalescing aggressively means you have a lot of virtual registers with extremely long life interval. This does increase register pressure. However, this goes back to the LLVM design philosophy. Every optimization pass does as aggressive a job as possible. So the rest of the coalescer expect the allocator to do the right thing by spilling life intervals at the right place to minimize the cost of spilling. And where the copy is coming from, as you can tell early on, a lot of copy come from two address elimination and mostly phenose elimination. These can provide a useful kind of guide to decide where to split life intervals, but they're not quite right. Any kind of heuristic is going to miss important cases. And to be frank, at this point, because we do coalescing before allocation, we don't really know the true register pressure. So we cannot rely on any heuristics to always do the right thing. So we rather over-optimize and hope later pass deal with it. Let's move on to the meat of the allocator. That's a linear scan allocator and the spiller. The linear scan allocator is very easy to understand. It does a single pass over all the life intervals, ordered by, in a fixed number, ordered by their starting point. Here, let's take an easy example of mapping 5 virtual registers onto a hypothetical CPU with 3 physical registers. The first 3 virtual registers get the 3 registers right away, no problem. The fourth one also locked up, no problem, because R3 has life interval has finished, so R3 is available again, so it's assigned R3. But V5 comes along, it wants a register, and clearly it overlaps with V1, V2, and V4, and spilling is required. How does linear scan deal with spilling? It does by picking a spill candidate, which are the life interval you overlap with. Look at the spill weight. The spill weight is roughly the number of depths and uses kind of weighted by the loop depth divided by the length of the life interval. So it picked the one with least use density, and it backtracked to the starting point of the spill victim and spill the life interval. In this case, let's assume we picked V4 to spill. we split it into a number of smaller intervals. For simplification reason, that life interval is only broken down into 2 parts, and they don't overlap with V5, and the Resocator can do all its job without any additional spills. Later on, we'll take another example to look at the issue with backtracking. So the linear scan and spiller kind of share the responsibility of spilling. The linear scan pick which life interval do I want to spill. And the spiller goes ahead and decide how that is spilled. And all the spill code is done later on in the rewriter after all the allocation is done. And this is a major problem. The bookkeeping is required to keep track of what's happening and where to insert spill code and all that is a major bookkeeping nightmare. We'll deal with that a little bit later. Last pass that's involved in registration is called the rewriter. The rewriter has a simple job, so to speak. It rewrites virtual register to physical register. All the decision has already been made. It should be pretty simple. In this case, in this example, we see allocation decisions being made, and we rewrite them into physical registers. The only thing worth noting here is the rewriter also is responsible for inserting spill code. And in this case, you notice V4 is also allocated a spill slot. So insert a reload before it's used. Now we'll talk about some of the optimizations that I find interesting in the Resocator. We'll take a quick look at the Coalescer. There has a lot of optimizations. We'll take a look at 2 that I find interesting. In this example, we have a single copy in the basic block, V1 to V2. But notice V1 and V2's life intervals, obvious overlap. We cannot coalesce them. However, we know the add instruction in this case is commutable. We take advantage of this property by commuting it. Forward substitute V1 to V2 and turn the copy into identity copy, and we can eliminate that copy. Another issue the Coalescer deals with is subregisters. For x86, there are, and so some other architectures, they are registered, they are part of a larger register. On x86, for example, AL, AH are subregisters for AX, and AX itself is a subregister of EAX. LLVM has pseudo instructions that deal with these subregisters. In this example, we take a look at extract subreg. So extract subreg V1 and 2, meaning extract subregister 2 from V1. The Coalescer treated as just like a copy. It coalesces, propagate the subregister index onto the use operand. The rewriter then take advantage of the information and extract our subregister 2 from EAX later on and turn that into AX. So everything just works. So spelling. We talked about spelling a little bit before. Let's take a closer look. So in this unoptimized case, spelling is very expensive. You can tell we have inserted 4 load instructions and 1 store instruction. And the 3 loads in the basic block can be very detrimental. We're loading the same values 3 times in the same basic block. So one optimization we put in is called folding, spills, and reloads. For x86, there are instructions that fold, loads, and stores. In this first example, we turned the single add instruction and the surrounding load and store into a single instruction. And the 3 other loads can be folded into the uses as well. Now, not only does this get rid of number instruction, this has an added benefit. We don't have to create new life intervals for the spills and reloads. This means we don't have to worry about additional spills as a result of this spill. But notice we're still loading the same value from stack 3 times in the same basic block. We can use life interval splitting to deal with this. Assuming we insert a single reload instruction in the basic block before the first use, then we can share the value with the two other uses. That we reduce the number of loads to 1. However, the new life intervals can still cause high residue pressure. It may want to be spilled again. No problem. We'll spill it as normal without additional stores because the value hasn't changed in the basic block. So the key point here is life interval splitting will not pessimize your code. In the worst case scenario, it does spilling just like the non-optimized case, but sort of in multiple steps. Go back to the machine LLVM example. I want to introduce a concept called rematerialization. We have hoist v set 0 into the loop pre-header. And we notice this instruction doesn't have any side effects. In fact, doesn't have any operands. We can recompute this value anywhere. So we're going to recompute the value before it's used. This is called rematerialization. This eliminates the need to do a reload. Load goes away. And if there are no other uses of the spill value, the spill goes away. And the definition that's hoisted into the pre-header goes away as well. Guess what? We're back to before LLVM happened. No harm done. So this is what I talk about. The later pass can deal with aggressive optimization the earlier pass has done. So we make sure no pessimization happens. We want to take a step further. Notice we can only do rematerialization currently on very simple instructions. We can only deal with instructions that basically have no register operands. That's not ideal because we need additional information to decide when is a good time to do rematerialization. Let's talk about generalized rematerialization. Let's just suppose we have hoist a pick load of a global variable into a pre-header. We want now to rematerialize this before its uses. If we don't have availability information, we can do this pretty naively. That means rematerialize the load that gets the address of the global variable, then rematerialize the load to read actual value. But notice that's 2 loads before every use. That's worse than spilling. However, if you have the correct alias information and have correct availability information, we may notice, for example, the value of the global variable is available in the second use. That allows us to get rid of one of the loads and may make rematerialization profitable. So the key point here is not only do we need alias information to be able to code motion, loads, and anything that touch memory, we also need availability information to do really good rematerialization work. Unfortunately, that information is not quite yet available, so we don't do this yet. The last part of my talk will focus on the work we're doing right now and some of the work we are thinking about or have in the plan. What are the goals? Well, we want faster compile time and generate better code, and we want to make the compiler more maintainable and flexible. These are not conflicting goals. We can really do this. It's not easy, but that's our plan. First thing we want to look at is called strong fee elimination. Earlier, I talked about the fee elimination and how naive it is. This simple case illustrates the issue. We have a fee node with 2 incoming values. The current fee elimination insert a copy in each of the incoming basic block. With strong fee elimination, it takes advantage of dominated information and some other information to eliminate the copies that are unnecessary. It coalesces them ahead of time. This means less work for the coalescer. This is good for compile time. The next step we want to tackle, the next thing we want to tackle is called iterative splitting. Let's assume, well, we want to be able to split arbitrarily and iteratively. Let's assume we split the life interval or something at the loop boundary. Now let's assume the newly created life interval still require additional splitting because it's used in the whole loop. We can do the same thing we do right now. It's splitting the basic block boundaries. However, if there are multiple uses in the same basic block, and the basic block itself is large enough, it may create more register pressure, but then we can spill in the intra-basic block. Insert a reload before a number of uses are somewhat close to each other, then we can share the value of the reload. This is what we mean by iterative splitting. I think this has a great potential of dramatically improve our performance. We also want to tackle aggressive rematerialization, not just generalized rematerialization. Let's take a look at yet another example. In the we have hoisted a number of load address computation into the loop preheader. We can rematerialize them here easily if we have the correct availability information. If we know X, in this case, is available inside a loop. So this is rematerialization. It at least make sure we don't spill. But we can take a step further. We can apply additional optimization on this. We have recognized there are some potential sharing possibility here. There's a loop invariant, IV, and there's X, which is available inside a loop and doesn't get changed. Then we can reassociate some code and enable even more sharing. These are the kind of things allow us to do very aggressive optimization in earlier phases. Finally, let's take a look at the backtracking and linear scan. We talk about linear scan. It's trying to maximize use of physical register resources, and it has to spill when we run out of resource. However, to spill a value, that means we have to reload the value back into a register. And to spill something, that means we have to first compute the value, which go into a register before we store it. So this is some kind of conflicting problem. And the way that linear scan deal with this is through backtracking. Again, our favorite hypothetical 3-register machine. V1, V2, V3 gets the 3 registers, no problem. V4 comes along and it conflicts with all three of them. We have to spill. The way it does is with backtracking. It picks V4 for spilling. It backtracks to the starting point of V3. Break it up into multiple smaller life intervals. The first life interval gets R3 right away. Now we're on to V4 again. V4 is now no longer conflicting with R3, so it gets R3. The second part of the spilled life interval comes in. Unfortunately, it conflicts with V1, V2, and V4. So again, we need to spill. So we backtrack again to the top, to the starting point of V4, undoing the rest allocation there, split it, and this allows rest allocation to go to a completion. You notice an obvious problem. Backtracking means we are constantly undoing and redoing allocation we have already done. This is very bad for compile time. We want to add the ability to spill previously allocated life interval without having to backtrack. This means no more linear scan. We don't want to be allocating in a fixed order. We want to jump to any life interval and allocate for that life interval. We believe an iterative approach and using some kind of priority to decide which ones get to allocate first is the way to go. And this will allow us to fix the backtracking problem. To summary, there's a lot of work to be done. We want to do smarter fee elimination for faster compile. We want to kill off backtracking by using iterative approach. We want to improve maintainability by insert spilling on the fly rather than wait until the end. This removes much work the rewriter has to do. We want to put a lot of effort into improved spilling. We want to be able to split iteratively in arbitrary places. We want to use availability information and alias information to do really aggressive rematerialization. And we have some other crazy ideas we are thinking about, such as rescheduling to reduce register pressure. And that's the end of my talk. Questions? Yes, we do. So the way we do we do res allocation on x87 stack? Yes, we do. We basically have pseudo register class that represents the x87 registers like normal registers, which means random access. Then we have basically turn them into stack operations in a later pass. Yes.
Are there any special considerations for vector registers?
Are there any special consideration for vector registers? No, we treat them just as normal registers. Yes.
Is there a point at which you're working so hard to undo all the work that you've done before that you might be better off having the other stages more integrated?
Is there a point where we're redoing all this work that it's better to integrate all the works into the res allocator? Are you talking about the interaction between the res allocator and the spiller? There is a possibility. For example, it's possible to fold some of the to-address computation into perhaps coalescing or the phase that deal with life interval kind of computation. A lot of things can be folded. Yes, the current structure served well enough, so we're not actively working on it.
You're saying that currently the selection tag sounds like optimizes is trying to choose to reduce register pressure for the register allocator. Is that something you'd like to be able to remove if the register allocator was?
I don't think that's quite the case. There's only so much the res allocator can do. So
can you say something about why that's different? Why does the register allocator, the DAG selection algorithm need to preview some of that?
So the scheduler actually does try to reduce register pressure for x87 where the register resource is extremely constrained. So the res allocator can't really deal with can only do so much. So there's a trade-off of scheduling for latency and there's a trade-off scheduling for register pressure. We found from our experiments that for the more modern x86 implementations, scheduling for latency doesn't really offer us all that much. Okay, there's the kind of dynamic scheduling engine in the CPUs work well enough. So we concentrate on reducing register.
Does the graph coloring approach for register allocation take too long or produce worse results?
My personal opinion is no single heuristics algorithm is the best. It's all sort of in the implementation. So we put a lot of thought into the implementation details and do all this optimization to get performance. The graph coloring, there are many.
For example, we can have light intervals on AR and 100 hertz. So they need to be
So the question is about sub-registers like AL, AH. Can they kind of are we taking advantage? They don't overlap, and so we are somewhat conservative in that. So a lot of cases, but we do check if two physical registers overlap. If that's the case, we know that. So the res allocator is taking advantage of that.
Two questions. First, you mentioned that you do the spelling operation for Coalescing. So is that equivalent to
In a way, right? Because we have, with help of, basically, yes.
So
yes.
For example,
so
sequence of copies all from the same register and registers, coalesce the first one, you still don't consider it interfering.
right. So basically, the question is whether variable numbering let us not having to build an interference graph. That's part of it, right? That's right.
Okay. And the other question, so for coming back to the vector question, so one issue that arises with vectors is you have multiple writes. You can have emphasis on vector before. Do you do anything to choose registers in that case? Make register choices that are far away, so you prefer small
The question is, some vector operation can implicitly write parts of, update parts of the register, and therefore depend on early operation. So we do live variables analysis time. We pay attention to a lot of these partial dependencies if they are explicitly represented. So I'm not clear on whether we do enough of that. As far as the rest allocation goes, we don't do enough of choosing this register over another one. There is a way to define the order of allocation preference, but that's sort of kind of my idea of what's best in a lot of ways. So you can ask me a question offline. Thank you.